exactly quantum, and they are not groups. They are deformations of algebras of functions in groups. They are full algebras. So first, let me give a short introduction to the algebraic structures I'm going to talk about. So the first structure is bialgebras. So let's start from the very beginning, and I'll have this list of algebraic structures on the left, and the properties of category of models over these algebras on the right. So first, natural structure is an associative algebra, say, over some base T. Then the category of models over A is an abelian category where objects are vector spaces together with homomorphism of algebras from A to endomorphisms of A. And morphisms in this category are A-linear maps between vector spaces. So linear maps that commute with the action of A. Now,
that only has the structure of a abelian category.
Yeah, that's the only structure it has.
Yeah, the maps, you can add maps.
Yeah.
Category, we can add maps.
Yeah. Now, bialgebra has more structure. Here's the formal definition of the bialgebra. This is an associative algebra A equipped with the following data. First, there is a linear map from A to its tensor square, such that it's a homomorphism of algebras, and it is co-associative. Co-associativity means the following. This diagram commutes. Is commutative. Now, why it's called co-associativity? Because if you would have arrows in the opposite direction with the multiplication here, say here we multiply first two factors, here we multiply first last two factors, and then here is the usual multiplication. Then this inner diagram would be just the associativity condition for the multiplication here. And this outer diagram is the co-associativity condition. So this is the first piece of data, and the second piece of data is the co-unit. So epsilon is co-unit, and it's the axiom of the co-unit is dual to the axiom of unit. For unit we have M1A is equal to A for an associative multiplication M. And A1 is A. And dual to this, there are these properties. And finally, the co-unit is a homomorphism of algebras. It's a one-dimensional representation. Now, this is a formal definition, and the meaning of this definition is the following. On the category of modules over this algebra, associative algebra A, we have an additional structure, a tensor product of representations. So when we have two representations, the phi b and phi b is this structural map from A to endomorphisms of V, and when you have that representation W, then its tensor product is just the vector space V tensor W together with the homomorphism map, which is the composition of the homomorphisms for the individual factors, and this co-multiplication map delta. This is a homomorphism of algebras. These are homomorphisms of algebras. So the result is a homomorphism of algebras again. Now, the co-associativity of the co-multiplication gives the associativity of this tensor product. So the first new structure in this abelian category of models over the associative algebra A is that there is an associative tensor product of models. And finally, the second structure is due to the co-unit. Because of the co-unit, we have a canonical one-dimensional representation given by this linear map. And this is representation which is usually denoted by this identity module, and it has this property. If you multiply 1 tensor b and b tensor 1, you will get a representation which will be canonically isomorphic to the initial representation, this representation b. The reason for this is this property of the co-unit. So the morale is that once we have a bialgebra structure and an associative algebra A, we have this tensor structure on the category of modules, and the name for this structure is the braided, not braided, sorry, just monoidal category. So for bialgebras, modules, category of modules is the abelian monoidal category. Now, it is very natural to require this tensor structure. Well, just to look at the category of vector spaces, so the most natural, and there are many reasons why it's natural to have this structure. So, the next piece of structure is the following. Suppose that we already have a bialgebra A with the common multiplication delta. Then we'll say bialgebra is a Hopf algebra if there is an antipode from S from A to A such that S is an anti-isomorphism of algebras, so that it just there is an inverse of this and it switches the multiplication and the orders of multiplication. And it's an anti-isomorphism of bialgebras. So if you will take composition of S with the co-multiplication, you will have so-called opposite co-multiplication, which is different from the initial co-multiplication by this permutation map, which maps A tensor B to B tensor A. And finally, there is this
What is it marks there in the symbol after the delta?
Where? Here?
Yeah.
This is S inverse.
That's interesting.
And finally, there's this strange diagram which is part of the axiom, and we will see why this diagram is natural from the examples. Essentially, a typical example of a Hopf algebra is the algebra of functions on a group. And in this case, the antipode is the operation when you take a function and instead of function of x, you consider function of x inverse. So you can keep in mind the analogy with group structures. Bialgebras are something like functions on semi-groups. Hopf algebras are something like functions on groups. So this antipode map brings another new structure in the category of modules. So since it's a bialgebra, we have abelian category, which is also a monoidal category. This is because of this structure. And plus the antipode brings the notion of dual representations. By definition, right dual representation is the following. It's a pair consisting from the dual vector space to the initial vector space V, and a linear map, which is the composition of the antipode, and the dual map to phi. Say, when you have a homomorphism from one algebra to the other, if you will take just phi star of AB, because it's a dual map, it will be anti-homomorphic. So you cannot take just dual map. However, if you will take a composition with the antipode, because antipode is also an anti-isomorphism, this will be again a homomorphism of algebras. So this is why this is the essential notion. However, there is no requirement that the square of the antipode is the identity. This would be the case for the group algebras. However, in this case, it's not so. So, in for group algebras in general, you have the notion of left dual and right dual. And in general, they are different. Now, the structure which we have here is called rigid monoidal category, and more precisely, what we have here is an abelian rigid monoidal category. This property of the existence of Q is called rigidity in this context. So, why? Why is it called rigidity?
Go, man.
Well, it goes back to the other categories. I think this notion was introduced by Berkeley and Mill in this paper connection categories. I don't know. So, before I'll give a few examples, I want to introduce another notion, which brings another important structure on this category of models.
Do you think this somehow makes the representation discrete or something like that?
Probably in some cases. Somehow I never thought about the etymology of this word. It is probably because of the analogy of some algebraic analogies. So,
well, there's kind of a rigidity in semi-simple legal theory.
Yeah.
Right, and there's also this killing form, which related to semi-simplicity, which is like duality.
Probably, yes.
Yeah. So that's what you said. This is like the inverse.
But I mean, definitely, it's a much more general context.
Yeah, we get lost in it.
So now I can say about the very strange etymology of this word quasi-triangular later. But now just definition again and the meaning. So the formal definition is here. There exists an element in A squared such that it's invertible, and if you conjugate the co-multiplication by this element, the result will be the opposite map delta prime, which is the composition of the permutation map and the co-multiplication. And also these two properties which describes the action of the co-multiplication on the element R.
And what's sigma? We have sigma.
Sigma is the permutation map.
Second equations are consequences or assumptions?
No, these are all axioms.
For R.
Yeah. This is how R interpoints the co-multiplication, and this is how the co-multiplication acts on R. And all these properties, they have extremely simple meaning in terms of category of models. So because it's a group algebra, we are dealing already with the category of with the abelian rigid monoidal category. Now, this structure brings the following. It is a factorial isomorphism between V tensor W and W tensor V. So now in the category of models of quasi-triangular group algebras, there is this canonical so-called commutativity constraint. And the commutativity constraint in this case is given by the composition of the permutation map. So here P V W, it maps V tensor W to W tensor V, and it just exchange the factors. And RBW, it acts from V tensor W to itself. And W is just the result of the evaluation of this element R at the tensor product of two representations. So the name of this element R is the universal R matrix. And so the meaning of the last two actions is the following. The commutativity constraint is compatible with the tensor structure in the following sense. There is a nice pictorial way of thinking about the tensor categories. And what we have here with this structure is an example of a tensor category, or strictly speaking, quasi-tensor category. Because, so let's think about the modules over the algebra A as points on the line. Then you can think about commutativity morphisms. Say then tensor product is something like this, that you consider instead of one point, so the configuration of 3 points. And strictly speaking, you have tensor product of 2 representations. So if you have tensor product of 2, then you multiply to the third one. So you have these brackets, and then if you multiply these 2 and then multiply this one to the result from this side, you will have another configuration of brackets. So you can forget about the brackets because the tensor product is associative in this case. And you can think about commutativity morphisms as braids. Say, here you have the object, the representation which is the tensor product V2, V1, V3. Here you have V1, V2, V3. So this would be the picture for the commutativity morphism C, V2, V1, which brings V2 tensor V1 to V1 tensor V2. And then the last 2 actions, they have very natural meaning, because, say, when you have something like this, so this is V tensor Q tensor W. Then you can think about this configuration in 2 ways. First, you can think of these 2 lines as something representing one object in the category, which is V tensor U. So it will be the morphism C V tensor U W. On the other hand, you can sort of homotop this line to here, and you can think about this as a composition of 2 separate commutativity constraints. So this would be C.
What you have.
Yeah. Identity tensor C UW C W tensor identity. And well, the fact that this picture is considered modular this isotopes, you reflect it in this equation.
Collier, is your notation set up to distinguish between an overcrossing and an undercrossing?
Well, in this case, this commutativity constraint C is, well, let's call it overcrossing. If you have inverse, this will be undercrossing. So in general, strictly speaking, historically, tensor categories were defined by the leading Mill, and there they required this composition to be the identity map. The reason for this was because essentially they studied category of models over algebraic or pro-algebraic forms.
Probably these were defined more. The earlier sort of claim.
Yeah, actually, yes, that's right. they just sort of put it into this framework.
He made this mistake, so to speak.
Yeah.
This was his mistake. Otherwise, he would have discovered quantum consciousness in
Yeah.
61. Yeah, so now they can hook up the audio and make sure.
So this is the. So this is the. So this is the definition of quasi-triangular. Now I can tell you about the etymology of the word quasi-triangular. It's very strange.
Do we have the rate relation yet?
Yeah, that's what I'm going to say now. So one of the remarkable property of this element R is the following: that if you have such an algebra, then it is almost immediate corollary of these axioms that it satisfies so-called Yang-Baxter equation. And so I didn't explain the notations there. So here and there, this R12, R13, and R23, they are elements of A cube. And this is just R tensor 1. This is 1 tensor R. And
Can't write.
This I can't write, yes, but I have a trick. This is identity tensor sigma. Remember, sigma is this permutation. R12. Sigma.
You want to put a sigma back in? Don't you want to conjugate by
No, it's a sigma acting on this R.
Yeah.
It's a sigma acting on R tensor 1. So this is called Yang-Baxter equation, and one of well the.
But you know, that can't be the right formula, right? I mean, you have to conjugate.
No, sigma is a map. A squared to A squared.
Yeah.
That maps A tensor B to B tensor A. It's this map.
Yeah.
So acting on R, it just switches it. Well, I can do. Yeah. All right. So, well, there is a long history behind this equation. So first, it was, well, I mean, people who were doing topology of knots and links just didn't realize that that they were dealing with this equation for almost, I don't know, 100 years and less. First, explicitly in this form, it appeared in the works of physicists. First, Young, who studied factorized scattering, discovered a certain specific solution to this equation, and Maguire didn't have sort of really matrices. He did have functions, but so he had one-dimensional solution, which is not interesting. I can write. Yes, but from the mathematical point of view, it's not interesting because you can take any function here. If it's one-dimensional, then it's trivial. So the non-trivial fact that there are matrix solutions to this equation, so to say. So from the physics.
It's a non-trivial fact.
I'll show you. Say, okay, let's first evaluate it in some tensor, in some representation V. So let's consider the case when you have RVV. Say you evaluate it in some. Well, just let's say the following. Suppose that we have here A as the endomorphisms of some finite dimensional vector space V.
So you have n cubed equations.
Yeah, you have
unknown, sort of.
n squared unknown and n U equations.
Yeah, okay.
So if n is greater than 1, then so the very first appearance of this equation was in this physical context, when basically I hope physicists will not try to correct me because I will be cheating slightly now. So the
That's not fair. You can't correct it. We want to learn the truth.
No, but I love him to swindle an audience of mathematicians. So I'll enjoy this.
So, there is such a notion as scattering in classical and in quantum mechanics. So, it's not completely fair to think about quantum mechanical particles going, say, along some trajectories. But it's a good intuitive way of thinking about it. So, when you have factorized scattering, that means the following. Let's say, suppose that you have three particles moving along their sort of phase lines, and say they collide in here. So this point represents their interaction. So then the factorizability of the scattering means that this three-particle process is essentially a composition of two particles once. So schematically you can write it as, it's something like the resolution of singularities. So in this case you can do it in two ways if you don't want to break the lines. So now if you will say that this matrix R describes this two-particle scattering, then say if this is 1, 2, 3, and this is 1, 2, 3, you have to put R2 here, R1, 3 here, R1, 2 here, R2, 3 here, R1, 3 here, and R1, 2 here. And if you read this equation from, yes, according to the time flow, you will have exactly this identity of the compositions.
It's a great way to remember the equation.
Yes.
You can't forget it.
Exactly. So, so this is called, now it's called Young-Baxter equation, because Baxter then sort of very successfully applied this equation to certain extremely interesting models of statistical mechanics, and he found more solutions to this equation, more matrix solutions to these equations.
You could point out that the first solution of these was found by Untitled in 45, 44.
That's right, yes. The first solution was found by Anzager, but it was in quite different way. Yes. Yeah, as I said, this equation was known for a while. And in fact, I don't know, Burau representation to the braid group probably appear when it...
Well, that's pretty old.
So probably that was the first solution to this equation in a sense.
Can I ask, well, that's a nice scattering matrix interpretation equation. What is there a nice sentence in this, I don't know what you call this theory. This theory you work on, lattice theory, that corresponds. What's the meaning of this equation in the lattice theory? It corresponds to something being well defined, something else being well defined.
This is what you need in order to make two very large matrices commute.
Oh.
Yeah, the corollary of this is so-called commutative.
No, but that's the practical reason. Isn't there a more physical requirement?
I would say.
This is what leads to the existence of, if you will, for a large system, an infinite number of conservation laws, which makes the system integrable in the sense of Lewis.
I think really, so from the physical point of view, the best way of thinking about this is in terms of this factorizability of the scattering. The rest is more artificial, probably.
And this contains the need of a spectral variable?
I don't want to talk about spectral variables, because this would be completely misleading. I mean, we don't need it so far.
It really becomes most powerful with the variables.
Yes. So this is the origin. And now I said that there is something about etymology of the word quasi-triangular here. So you can see two triangles here. So this is the etymology of the word. When Belevin and Drinfeld wrote their first classification of Lie algebras, they call it this equation triangle equation, because you have the equality of two triangles. So this is the etymology of this word.
Yeah, what about the quadrate?
Well, strictly speaking, what they were talking about when they first wanted to have solutions is something like this. They acquired this condition. So then Drinfeld developed this terminology. He said that this will be triangular solutions and this will be quasi-triangular solutions, where this is not necessarily one. So,
what words would the mathematicians use to put in the spectral variable?
Put in what?
In general, those R's depend upon a variable, and there is a connection between the three variables. So that's what makes it powerful for what factor it is.
There is a
parameter.
there is a very simple meaning in sort of the appearance of parameters. Say, when you're talking just about general solutions, here you have two different vector spaces, V1, V2, and V3 in general. So you can put as many as you want parameters here. Now there are very special solutions to this equation related to very special algebras. There are solutions related to, say, finite dimensional simple Lie algebras and their deformations. They depend essentially on one parameter. And then there is another very important class of algebras, affine Lie algebras. They are central extensions of loop algebras. They also have some very special solutions depending on two parameters. And then there's generalization of this when you consider well, so-called elliptic solutions. They have three parameters. So essentially this is what is known. I mean, and the meaning of these extra parameters is exactly the subject of Monday's lecture. It's the subject of finite dimensional representations of these quantum affine algebras.
So this equation is 1. That corresponds to the commutativity AB composed of BA is the identity.
You mean when it's 1?
Yeah. This condition, that corresponds to the MacLane idea of the monoidal typical.
Yes, exactly.
Okay,
Yeah,
this is a special case.
Yeah, this corresponds to the case when
So these should be called braided triangular complex. It's like one is symmetric and one is braided.
Yeah.
Okay.
In fact, another name for these categories is braided Hopf algebra. For these algebras, a braided Hopf algebras, or the name for these categories is a braided monoidal category, abelian braided monoidal category. Well, they studied special case. They proved the following theorem, that once you have the theorem is the following. Suppose that you have a tensor category where, well, there is a functorial way to define dimensions of objects. And they call it rank of the object. And they proved the following, that if the following statement, every tensor category where ranks of objects are non-negative integers is equivalent to the category of modules over some pro-algebraic group. That's well, it was well before actually Young-Baxter. I mean, it was before the name Young-Baxter equation.
Let's say 67.
It was 70 something, I think.
So it was well after Young-Baxter.
It was well after Young-Baxter. Yeah. Baxter, I guess, did it in 72, and Young did it in 67, I think. So.
Anyway, it doesn't matter because the point is not the same at all.
No, absolutely. I mean, they're completely.
They're getting a group out of it.
Mm-hmm.
They're saying the category module over a group is characterized by some of the properties that you're talking about in a certain context.
Well, what they proved is some kind of reconstruction theorem.
Huh?
Well, some kind of reconstruction theorem.
Reconstruction.
Yeah, reconstruction of the
Yeah.
group. I mean, the whole point of this is that there are objects that go beyond groups
Yeah.
that have these properties.
Yeah, exactly.
The slightly generalized versions.
Okay, so now some examples. Well, as I said, the sort of typical example is when the algebra is the algebra of functions on G, then it's a very simple algebra. It's a commutative algebra with pointwise multiplication. And the co-multiplication in this case is given by this multiplication map in the group. And just to be precise, let's consider the case when G is either finite or, say, algebraic group. In this case, C of G will be, say, polynomial functions in algebraic group. Then this is true. So then the co-multiplication is given by the multiplication in the group. So co-multiplication acting on the function gives the function of in two variables, which is f of x, y. The antipode gives the function of x inverse, and the co-unit is simply the result of the evaluation of the function at the identity. Now, the other example of a Hopf algebra, which is so-called, well, obviously this is a commutative algebra, and as an algebra it's very simple. It has complicated co-algebra structure, but the algebra structure is almost trivial. So now let's G be a Lie algebra, say finite dimensional Lie algebra. Then there is a natural associative algebra related to any Lie algebra is the universal enveloping algebra. So you consider tensor algebra of the vector space G, and you consider quotient over the ideal generated by these elements. So this gives the vector space, which is isomorphic to symmetric algebra on the vector space G, and the algebra structure is described here. So essentially, this is the if you will choose the basis EI in G, then UG is the algebra generated by elements EI subject to the relation commutator of two elements is equal to this, where Cij, are structural constants of the Lie bracket in this basis.
Is G always injected into U of G?
Yes, UG then
I mean, for any Lie algebra, even if it's infinite dimensional, right?
well, if the Lie algebra is infinite dimensional, one has to be slightly careful about the definition of UG.
Well, with that definition.
Yeah. I mean, with this definition, it's obviously that it's embedded. There is Poincaré-Marcouf theorem, which says that there is an isomorphism of vector spaces as G, and essentially that means that, say, if you will take monomials, symmetric monomials in the generators E, then they form a linear basis.
True without any assumption on G.
Absolutely, yes. It's a general fact. So there is always this linear part in the universal enveloping algebra G. So the space of linear elements.
The ring structure, though, is not the obvious ring structure on S of G. It's highly non-commutative.
Yes, of course. Just this is the isomorphism of vector spaces. So.
Dual to the other one, right? Function.
Yeah, exactly. That's what I'm going to say in a few minutes. So, in this case, the co-multiplication on linear elements is defined by this simple formula. It's just the diagonal action of G on the tensor product. So it's x tensor y plus 1 tensor x. And the antipode, again, on linear elements, is simply the map which brings x to minus x. And you can check with this relation that this is an anti-isomorphism. And then the co-unit is 0 on all elements except the ones that are proportional to the identity, I mean to the unit element. And it's 1 at the unit element. So now this algebra of functions on G was commutative. The universal enveloping algebra is co-commutative. Co-commutativity means that the co-multiplication is symmetric. So
if you will take the composition of the permutation with the action of the co-multiplication on the element x, or more precisely, if you'll take, do this. So this will be delta x. So, and now I'm coming to the question about duality. The fundamental property of the bialgebras is the dual pairs or duality. Let's say, here's the definition. Two bialgebras are called dual pair if there exists a non-degenerated pairing between these vector spaces such that the co-multiplication, the multiplication on this algebra corresponds to the co-multiplication on the other. And a multiplication in B corresponds to the co-multiplication in A. Corresponds means just the dual map, assuming that sort of we will say that B is a dual with respect to this pairing. And again, S tilde is dual to S, and then co-multiplication for the algebra A in this case will be the pairing between A and element and the identity element in the dual group. So you can say that co-unit in A is the same as the dual to the unit in B, and unit in A is dual to the co-unit in B. So with this duality notion, everything becomes symmetric.
Except there's one thing. I mean, every continuous group G has a Lie algebra, so you can perform both constructions.
Yes.
But every Lie algebra doesn't have a Lie group, so you can perform the construction on the left.
This is why I said it's a dual pair. I mean, one has to be.
So interesting. So the U of G construction is more general.
Yeah. Well, it's more general because it's sort of local.
The other is more general too, because some groups don't have Lie algebras, like finite groups.
You're talking about semi-groups, so infinite dimensions.
No. Well, I mean, just look at the two things. The two constructions have slightly different domains, right?
Algebra of function and the universal developing algebra.
Yeah. One's on Lie algebras.
Yes.
One's on groups. On all groups. Some groups have Lie algebras, but not all groups have Lie algebras, and not all Lie algebras have groups.
Well, the fact that some groups don't have Lie algebras, that's curable. There is nothing terrible about it. You just consider group algebra instead of the universal developing algebra.
Oh, I see.
Universal developing algebra is something like the group algebra of G in the neighborhood of the identity.
You have to do something else to the group algebra.
Yeah, you will have to squish the sort of group algebra in the neighborhood of the identity, and then it will become the universal developing algebra, roughly speaking.
So every group has a, so to speak, universal developing algebra.
Yes, so every group has its group algebra. So if you're talking about discrete groups, then instead of the universal developing algebra, you have to consider group algebra. And this algebra also has a natural Hopf algebra structure. So elements of this algebra are formal linear combinations of group elements. And then the co-multiplication is simply this, sum over G tensor G. And you can see that this is sort of the global version of this infinitesimal formula x tensor 1 plus 1 tensor x. And the antipode acting on this would be just bring G to G inverse, and so on. It is true that not every Lie algebra has a group. Well, that's a more serious problem. And but this problem also can be cured by considering formal group. We can always consider formal group in the neighborhood of the identity.
Formal functions.
Yeah, formal functions.
Okay.
Yeah. So when it's infinite dimensional, there are all sorts of topological problems, and there are all sorts of ways to solve these problems, depending on the context. So if it's a finite dimensional Lie algebra, and G is a G is a Lie group corresponding to this Lie algebra, then there is a natural pairing between these two. which is just the following. You can consider linear elements acting by left translations on the group, and so this gives the action of the universal enveloping algebra on the functions on group by differential operators.
So it's really a differentiation, right?
Yeah. Yeah, exactly. So essentially, this X has some differential operators acting on functions. Yeah. So this is the, and you take this operator, apply it to the function, and compute it at the identity, and that's the pairing. So in this sense, these two examples are dual to one to the other. This is a co-commutative algebra, this is commutative, and you see that the duality sort of explains why one is commutative, the other is co-commutative. So
I've heard all these things in bits and pieces, now it's all clear. Great.
yeah, unfortunately it's a rather long subject, but extremely interesting. So now I'll bring back to the question of deformations. So let me just say formally what I mean by deformations of bialgebras. I'll talk only about flat formal deformations. So B over of the ring of formal power series in H is called flat formal deformation of A over K. If there is this isomorphism of the modules of formal power series, and if the multiplication in B are denoted by this fat dot is equal, after fixing this isomorphism, we can compare the multiplications in B and in A. And again, and the co-multiplication. Again, we should have the multiplication in B is equal to the multiplication in A modulo H, and the co-multiplication for B is equal to the co-multiplication for A, again, modulo this formal variable H. So this is a very natural definition which generalizes the notion of deformations of algebras. And
which of the two adjectives apply to which part of the hypothesis? You have flat, well, formal somehow the power series.
A formal is power series. Flat means that there is this linear isomorphism, that B is a free module over power series in H.
So like the free module over power series.
So now if A is a commutative bialgebra, meaning that the multiplication is commutative, the co-multiplication is doesn't matter which one. Then we can define and suppose that we have a first order deformation of this commutative bialgebra. Then we can define these brackets. So then we can forget for a minute the structure of the bialgebra on A. So if you forget about the co-multiplication, what you will have here is you will have deformation of commutative algebra. And first order deformation of commutative algebra always brings a Poisson structure on this commutative algebra. So this gives.
Then the associative law will reduce to that.
No, I skipped the one sentence. So then A together with this bracket becomes a Poisson algebra. So remember, it's a commutative algebra. It's a Lie algebra with this Poisson bracket, and this Lie algebra structure acts by differentiation, by derivations on commutative algebra. So there is a Leibniz rule. Now, this is what we have just here. Now, if you will also have a coalgebra structure, then the first order deformation will require that, will mean that identity should hold. This is just the first order term in the co-associativity. I'm sorry, not in the co-associativity, in the compatibility. So delta must be a homomorphism of algebras, and the fact that it's a homomorphism of algebras after first order deformation means that this equation holds. And essentially what I wrote here is the definition of so-called Poisson-Hopf algebra. So now we have the following. A is a Poisson structure with this Poisson bracket. A is a Hopf algebra with co-multiplication, commutative Hopf algebra, and it's called Poisson-Hopf algebra if there is this extra compatibility condition for the Poisson bracket.
So the two dual compatibilities are just the residue of the associative law,
Yeah.
form structure,
Yeah.
associativity and co-associativity.
Yeah. No, compatibility between co-multiplication and multiplication. This.
Oh, that? Oh, yeah.
This is
Oh,
the.
that's just the,
This is
the ring,
this.
the homomorphism.
Yeah.
of
Yeah.
an infinitesimal homomorphism.
Yeah. This is an infinitesimal. This is a homomorphism of this infinitesimal algebra structure. So now
What is associativity and co-associativity?
it's just this. This is a Hopf algebra with the co-multiplication delta, so the usual co-associativity requirement for delta, and it's a commutative algebra, so the usual associativity for the commutative algebra structure.
You see the line of my question. I mean, this third property here, that comes from the statement that the deformed algebra is associative to the first order. Isn't that right?
Yeah.
Right?
Well,
The third one.
I would say these two.
Oh, it's the Jacobi identity for the Lie algebra.
Yes. In the first order, this is the associativity condition. In the second order, it's a Jacobi identity, which follows from the associativity.
If you have a deformation of algebras, the first order, you just see the Poisson structure.
You just see
You
this.
see this bracket, right?
Yeah.
And then it has these two properties.
You see the Leibniz rule. That's the first
You
order.
see the bracket also.
Yeah.
You see
The
Poisson bracket.
the bracket and the Leibniz rule for the bracket in the first order. If you expand
Oh,
it to
but you
the...
don't see the Jacobi identity.
No.
That's in the second order.
Yes.
Okay, so then this.
So this is H.
Oh, this is the analog of the. So then what's this? This is the.
This is the analog of the Leibniz rule for the compatibility condition between the multiplication, the form multiplication, and the co-multiplication.
So it's the first order again.
Yeah.
And what's the dual of the other of the Jacobi identity? It has to be totally symmetric, this discussion.
No, well, let me... So when you have a Hopf algebra, when you have a bi-algebra, you have vector space, multiplication, and the co-multiplication.
It's not symmetric because it's commutative, the algebra.
Well, so associativity, you can write it like this. Say, you can think of multiplication as the trivalent graph which brings A and B to the AB. So you can. So this is the associativity. Now, similarly, co-associativity, you can think of this. You split an element A into two pieces. And
Read upwards. Read those. Read those trees upwards.
Yes. So these are the sort of the top of the bush, and this is the root of the bush. And now the compatibility between co-multiplication and multiplication is unfortunately rather inhomogeneous property. It's, if you think about this in terms of diagrams, you have something like this. Say, the left side would be the following: delta AB. This is the left side. You take element AB, multiply it to AB, and then you split it using the co-multiplication into two tensor factors. Here, this side is delta A, delta B. You see that there are two co-multiplications here, and you multiply in A squared, so there are two multiplications. So what you do here is you first split it into two pieces, and then you multiply it using the multiplication. So these two are symmetric. However, this one is quite different from this and from this. And what I have here of this relation, it's different from these two, basically for this sort of heuristical reason. So, what? Here? Well, I didn't have place in the bottom, so it's here. It's delta A, delta B.
But don't you then have to bring in?
And the compatibility is delta AB is equal to delta A, delta B.
And the reason it's two arrows is because you're in the tensor square.
Yeah.
This is the equation in the tensor square.
Yeah.
So it's got two. That's why there's two things. That's
Yes, exactly. Okay, now, so we have this notion, or we have this notion, Poisson-Hopf algebra. It's a following data. Commutative Hopf algebra A with the co-multiplication delta, and the Poisson structure on this commutative algebra that is compatible with the co-multiplication in the way I wrote it on the previous transparency. Now, this Poisson, suppose that we have as our commutative algebra the algebra of functions on a group G. So then Poisson algebra structure on the algebra of functions is the same as Poisson structure on the group as a manifold. So in this way we arrive to the following notion, to the notion of Poisson Lie groups. And the definition, formal definition is the following. G is a Poisson Lie group if it's a Lie group, if it's a Poisson manifold, and if the group multiplication, which is a map from G across G to G, is a map of Poisson manifolds, is a Poisson map. So this is a geometrical notion which is sort of behind this infinitesimal.
Is covariant or contravariant?
Well, Poisson tensor is the element of the second wedge of the tangent space. So they're covariant, yes. So I just want to. So we started with Hopf, with bialgebras,
But there is no map.
and then infinitesimal deformation sort of
Wait just a minute.
gives this Poisson Lie. Yes?
You can't push forward R vectors, right? For any map. Like a vector
Well,
field, you can't push it forward because the fiber could have many different points, and then there are many different vectors in the image. Right? What? Huh?
Well, the statement is the following. The multiplication gives a map between this manifold across G and G. And the property of this ether essentially is the following. That well, what is a Poisson map between manifolds? It means that the corresponding map between functions is a map is a Poisson algebra homomorphism, so algebraically speaking. And between functions, you will have the map in the opposite direction, from the functions on G to the functions on G cross G. And
I guess what I'm saying is that the derivation of an algebra is not a covariant kind of thing. I remember hearing Michael Arden saying this 35 years ago. Automorphisms is not a functor.
that's right.
That's a big problem. And these are infinitesimal automorphisms. That's not a functor either. But Blaine's saying you correct it just by saying it works in this case.
It's say when you have two Poisson manifolds, M and N, you may have Poisson map between them, a map which brings one Poisson structure to the other, sort of one vector field to the other, one two-vector field to the other. So what you have here is you have two-vector field on this manifold, two-vector field on this manifold, and this map gives you two-vector field on this manifold. Because well, I can. It's a okay. I should, of course, it's a very special case, and you're absolutely correct. Yes. Yeah. It's. I can write you infinitesimal condition for this Poisson
You
tensor.
could say that the pullback of the functions is kept invariant by the Poisson structure is a bunch of derivations of the algebra, right? So you can ask the sub-algebra
Yeah.
invariant, and there's a new Poisson structure
I'll just write it explicitly.
given one. Okay.
So this is algebraically, this is the linear map you have by sort of by pullback of this map. So in fact, I don't know what I'm
Well, see, we don't
what I
have to write
was.
the formula. It's just a conceptual point. See, the structure is given by a bunch of derivations, right?
Mhm.
The Poisson structure. And so you have all these derivations over here on the right, and you have this sub-algebra. You just ask that the derivations keep it invariant.
Yeah, the question
This
is.
the structure of the sub-algebra, and it be the structure given.
Yeah, what is the
thing
Poisson?
the point is there's not always an induced structure like you have a map. That's what we thought.
Yeah, so this is a very special case. Yes.
It works in this case. That's
Yeah.
part of that's what Blaine said. There is a transported structure is part of the hypothesis of being a Poisson manifold.
So essentially what is what is the Poisson structure here, and this very special sort of means that I have to define Poisson structure here, and then it will be defined. Then this statement will be well defined. So I have to, when I say that it's a Poisson map, I have a Poisson structure here, but I did here, and it's described by the following Poisson bracket on this space. If you have two brackets, if you have two functions, then the bracket is just f1 g1 f2 g2 plus f1 g1 f2 g2, or in terms of and on the other hand, this is the sort of eta on G cross G, G, F, G, G, F, G. I think it's something easy, but I just can't. So then from here you can compute what is the Poisson tensor here. It's a standard construction for the product of two Poisson manifolds. Standard tensor, standard Poisson structure on the product.
Okay. I understand that.
So now let's consider the neighborhood of the identity. There you have a Lie algebra. You can think of this as a tangent space at the identity, and the differential of the Poisson tensor at the identity becomes an element of the second which power of G and tensor product with G star. You can think of this map as a linear map denoted by delta from G to wedge squared of G. And this linear map will have the following property. It will be one cocycle on G with values in the wedge square of G. This will be the corollary of this compatibility condition between the Poisson structure and the co-multiplication. This will be the corollary of, sort of, roughly speaking, of this identity. And it will satisfy so-called co-Jacobi identity, which means essentially that the dual map, which will map from the wedge squared of G star to G star, will be a bracket. And this co-Jacobi identity is a corollary of what? It will be a corollary of the Jacobi identity for the Poisson bracket induced by eta. So now I moved from this infinitesimal structure for deformation of bialgebras to Poisson-Lie groups. And finally, I arrived to the notion of Lie bialgebras. So the most infinitesimal notion you can imagine in this case. And here's the formal definition. So if you have a linear map from G to second wedge power of G that satisfies these two properties, then you have a Lie bialgebra. And basically all these notions like Lie bialgebra and this quasi-triangular hoop algebras, they are due to Drinfeld. And he also noted at the very beginning this well, nice correspondence, which is sort of obvious, but quite remarkable, between Lie bialgebras and connected, simply connected Poisson-Lie groups. So if you have a Poisson-Lie group, you can always consider tangent Lie bialgebra, which is this linearization of the Poisson tensor at the this Lie bialgebra structure to the structure of Poisson group, and it's unique if the group is connected, simply connected. So now I want to state.
Like delta could be 0, right?
Delta could be 0. Yeah, that's the easiest example. If delta is 0, you have a trivial Lie bialgebra structure on the Lie algebra G, and it's the easiest case. The other cases are when the Lie bracket is trivial, and when delta, then that means that G dual is a Lie algebra with trivial one cocycle delta. So again, as for bialgebras, there is this duality. If you take a vector space which is dual to G, say if it's a finite dimensional case, then the statement simply is that on the dual space you have to G you have a natural Lie bialgebra structure induced where the Lie bracket is induced by the map, where the Lie bracket is simply the map dual to G, and the Lie co-bracket is the map dual to the Lie bracket on G. So well, now I can say what quantum group is. Now let's read this story in the opposite order. And let's start from the Lie bialgebra. So once you have a Lie bialgebra, you can construct two things. First, you can consider this connected, simply connected Poisson-Lie group G with the induced Poisson bracket. Second, you can consider universal enveloping algebra of G, and this one cocycle delta on G will induce one cocycle on the universal enveloping algebra. But now G was one cocycle for the Lie algebra, this will be one cocycle for the associative algebra. So it will satisfy this identity. And it will be completely determined by its value on linear elements. And on linear elements, it's given by delta.
So it's just a derivation of the universal developing algebra? Square 0 or something?
Not quite derivation, because it could be derivation if it would have values in UG. If it would have values in the algebra itself. It has values in A squared. So I should have, I was slightly not careful here. I should put here delta x and here delta y, meaning that where delta is the diagonal co-multiplication for the universal developing algebra. It's one co-cycle with coefficients in the tensor square of the algebra. So then quantization of this algebra, so strictly, well, quantum group corresponding to this Lie bialgebra is a bialgebra deformation of this Hopf-Poisson bialgebra such that the multiplication on this deformed algebra starts with the commutative multiplication plus and then terms of order h squared. And the co-multiplication starts with h squared. It's a special deformation. Dual picture is the following. You take the universal developing algebra and then the multiplication is deforming in such a way that the corrections will be of order h squared and the corrections to the co-multiplication will be given by this one co-cycle delta. And there's a duality here, so there will be duality here. And these objects are called quantized algebras of functions, so abbreviation quantum groups. And these objects are called quantized universal developing algebras. And unfortunately, there is also abbreviation for the same objects, quantum groups. There's actually intrinsic reason for this identification of abbreviations. I noticed that here that somewhere a few minutes ago, that once you have a Lie bialgebra on its dual vector space, there is a natural Lie bialgebra structure. So you can have the same picture for the dual Lie bialgebra. And there will be natural duality between these two pictures, for G and for G dual. And the quantized universal developing algebra for G will be something sort of morally speaking the same as the quantized algebra of functions on the dual Poisson-Lie group. And vice versa. This quantized algebra of functions on G will be more or less quantized universal developing algebra of the dual Lie bialgebra. So there is a remarkable fact. After this quantization, after this deformation, there is practically no difference between the universal developing algebra and between the deformation of the universal developing algebra and between the deformation of algebra of functions. So there is sort of one object. And it's, well, there is something remarkable in this, because that's sort of various dualities after this deformation becomes sort of something like you take one point and you take the other point of the same family. And many dualities sort of can be thought in this way. In particular, I will talk about, I will mention next, during the next lecture, how Langlands duality, say the affine Langlands duality, enters into this picture for affine Lie algebras. You have to tell me when to stop.
Don't stop.
Okay. So, okay. So this is really sort of the summary of all these notions I introduced. And now there's a technical question, very important one. Well, the very first question is whether it's always possible to make this deformation. And the second question is, when it's possible, how to describe the deformed object in some reasonable terms. So the historically what happened was there were several examples, and in fact very important examples, given by specific formulas. And then a few years ago, Ettinghoff and Kashdan, they proved the general statement that any finite dimensional Lie algebra can be deformed in this sense, can be quantized. Unfortunately, their construction is, it's very nice in the sense that it's very functorial. What they actually do is they deform some category. The drawback is that it's very inexplicit. It's basically the existence statement and the statement which is more than existence. It's a very nice construction because it's functorial. It says that once you have a functorial in the sense that when you have two Lie algebras with a homomorphism between them, then there is a homomorphism of deformed object. However,
The deformed object is sort of unique then.
yeah, well,
At least
it's
canonical.
yeah. In this sense, this construction is canonical. Their construction is canonical. So the question, which is, I think there is still a problem here. The problem is the following. There is this, as we know now, there is this nice canonical construction by Maxim, which is Kontsevich, which uses the quasi-isomorphism between certain differential graded Lie algebras. So and it's a very explicit in the sense that it's an explicit formula for deformed multiplication. So the question is whether something like this would work for Lie algebras. Well, the answer is still, this question is still open, although there are some thoughts and conjectures. So,
It's not a math question. It's not a math question.
There is a math question related to this. Math question is the following. Say, you have canonical construction by Kontsevich, which gives you quantization of Poisson manifold. There is another canonical construction by Ettinghoff and Kashdan, which does the same. So you have two canonical constructions. Question: if they are not identical, then how to describe a path in the sort of corresponding Poisson manifold, which sort of brings this construction together? So there's this, there's this known fact that, say, the space of, I think it's, again, due to Maxim in this context. Say, when you have two Poisson manifolds, then the space of deformations of this sort of the two star products, they differ on some formal path in the space of Poisson structures on G. So the question is how these two, essentially, sort of, without going into the details, math question here is how these two canonical constructions are related. So,
Is there a uniqueness theorem in your context?
no. There's an explicit canonical construction which uses this categorical. It's actually simple. It uses this categorical language, but it's natural. But there's
So
no.
they don't know whether or not there might be an inequivalent canonical construction.
Well, an equivalent canonical construction would mean that there is some canonical sort of vector field in the space of Poisson structures, which would bring one construction to the other. It's possible, but
No. They make it because do they know that there's at most one deformation up to equivalence of a Lie Poisson algebra?
again, at most one deformation.
Well, it's the natural question of uniqueness in this problem.
They-
Equivalence. Kontsevich says yes. This is the context, the group context. Is it unique in this context?
What do you mean by uniqueness? Star quantization is not unique. When you have a Poisson,
Unique up to equivalence in Kontsevich's context.
No, it's unique up to a certain formal path in the space of Poisson structure. So basically it says the following, that any deformation is a composition of some canonical deformation and some deformation of Poisson structure. So the question is, say, when we have two deformation of Poisson structure, and so, well, this is the end of the functorial part. Now there will be a bunch of generators and relations. So now here's the example which was constructed before the general statement. It was due to Deinfeld and Jimba in this generality. And I mean, this story goes back to the theory of quantum integrable systems, but sort of what I will say now is the resulting outcome. So first I would like to, and then on Monday I will be talking about, so let me first say sort of the guideline to the next talk. So now we see that there is this correspondence between these algebraic structures and these infinitesimal geometric structures, Lie algebras. And somewhere in between we have these intermediate structures, Poisson Lie groups. So on Monday I'll explain how quite complicated category of finite dimensional modules over quantum affine algebras can be studied using sort of Poisson geometry. And more precisely I will construct certain simple Poisson algebra, certain simple elements in this Poisson algebra, and there will be a statement that the ring of isomorphism classes of finite dimensional modules is isomorphic to the centralizer of these specific elements in this simple algebra. Well, so this will be next time, and I will say more precisely what it is. So, but the main idea is that we'll use these Poisson structures to study the isomorphism classes of algebraic structures. So now a few more definitions. Now, Kac-Moody algebras. Let A be a generalized Cartan matrix. Essentially what it means is that it's a finite dimensional matrix, n by n matrix, with the diagonal elements being equal to 2, and off-diagonal elements have this property. They are always, I forgot about 0 here. It's either 0, -1, -2, or any non-positive number. And this extra property that Aij is non-zero if and only if a transposed element is also non-zero. Aji is non-zero. And I will assume that this generalized Cartan matrix is symmetrizable. In other words, there is this sequence of non-zero integers such that they intertwine the Cartan matrix and the transposed one.
So the indices are finite or
this is a finite set. Now the Kac-Moody algebra is the following. It's a Lie algebra generated by the elements EI, I, and HI, where I 1 to n. And another set of elements DI, where, well, it's not I goes 1 to n. So here R is the rank of the Cartan, of this generalized Cartan matrix A. And just the way how I will write these relations, there I assume that, say, first R rows of R are linearly independent. This is not necessary to assume this, but it's just for notations. The Lie algebra generated by those elements subject to these relations. The H and G elements commute between themselves. Then H elements bracket with E given by these formulas. H with F is inverse. Here's another bunch of brackets. And perhaps not most essential, but very important relations are so-called generalized SER relations. These are the following relations. So I because it's clear that what they do is simply they act by derivations. Now the meaning of this elements T is the following. If you will just consider the algebra generated by H, E, and F, you will have a Lie algebra. And elements H, they generate something like a Cartan subalgebra. However, there will be no non-degenerate bilinear form on this Lie algebra. Only if you will include these derivations T, there will be non-degenerate G-invariant bilinear form. And this is the reason why these elements are there. And then standard Lie algebra structure on this, well, there are many Lie algebra structures on this Lie algebra. Well, here is the one which is called the standard one, is the following. This co-cycle vanishes on the Cartan part. It also vanishes on elements T, I just didn't write it there. And it acts on elements E and F in this explicit way. So this is the definition of Lie algebra, standard Lie algebra structure on the Cosmode algebra. And now here is the explicit description of the quantized Cosmode algebras. Now I define this algebra as the algebra over K, Q, Q inverse. In order to have this formal flat deformation, UH, GA, which I was talking about earlier, one has to do simply the following. One has to set Q equals e to the H over K. So one has to complete this this ring by power series in Q minus 1, for example. Then it will be the same as power series in H. And one has to say that Ki is equal to e to the H di. Hi and Li is equal e to the H di. Then once you will complete it in the power series over Q minus 1, then this algebra will become the flat deformation of the universal enveloping algebra. And here you can see the explicit, terribly looking relations, but in fact they are quite remarkable. And they are quite remarkable because of the following. In terms of these generators, subject to these relations, there's a very simple bialgebra structure, which is given on generators of this algebra by these simple formulas. And so you don't have only existence theorem, you have explicit description of the deformation in this case. And here I should notice one thing. The way how this algebra is described is not via star product. It's something like embedded deformations. Star product is something like intrinsic structure on the object. This is something like embedded deformations when you embed this when you consider, say, free algebra generated by these relations E, F, and H, and D, and then undeformed universal enveloping algebra correspond to one ideal over which you mod out sort of undeformed relations, and then deformed relations, you deform the ideal, so you so the non-trivial fact here is to prove that you will end up with the same vector space, and so this deformation is flat. So, okay. Now, a few more facts about this algebras. Well, first, a very important statement. This algebra UQ GA, quantized Cosmodi algebra, is in appropriate topological sense a quasi-triangular Hopf algebra. You see that not only, I mean, the fact that universal enveloping algebra is infinite dimensional is not surprising, but I mean, it's always infinite dimensional. In this case, it's not only infinite dimensional, it's also infinitely generated. So this is quite a big space, and the element R, which is supposed to be here in the second tensor product of this algebra, it's not actually there. It's in certain completion of this tensor product. And I'll talk about this next time. I just don't want to talk about it now because it will be quite a long discussion. So this is the first important fact. And the second important fact is about simple finite dimensional algebras. Say, if the Cartan matrix A is non-degenerated, then you know it's a Cartan matrix of some simple finite dimensional, some simple algebra. Then in this case, there is a nice fact that there is an isomorphism of algebras between this deformed algebra and the undeformed algebra over the ring of formal power series, such that it preserves Cartan subalgebra. And once you know this, well, you basically know that the representation theory of this algebra is the same as the theory of the undeformed one. Because what's the basic question of the representation theory? You count sort of first question, how to describe irreducible representations. Second question, how to describe sort of multiplicities of irreducible representations and given representations in the semi-simple case. And the third question is how to describe weight multiplicities in the irreducible modules. And since this isomorphism preserves Cartan subalgebra, you have answers to all your questions just the same as for the usual one.
So in that case, quasi-triangular becomes triangular?
No, quasi-triangularity has something to do with the tensor product structure. You see, this is the isomorphism of algebras. Yes, as a co-algebra, it has very non-trivial structure.
It's still there.
Still there. And in fact, as a co-algebra, it gives all these all known Vassiliev invariants, for example. However, this is not the case. Say, the reason why I introduced the algebra UQG with letter Q here is the following. If you will consider this algebra over the polynomials in Q minus 1, and then say if you will localize it at some real non-zero value of Q, then one can consider, say, some real forms of these quantized universal enveloping algebras, which will be star Hopf algebras. They will be star algebras with some real involution, but this involution will also preserve the co-multiplication. So, in this case, you can ask the question about unitary representations. And this question is very simple for compact forms of G. And it's just finite dimensional representation. Is not. However, if it's a non-compact form, real form, and there is such a notion, then there is a very interesting phenomena. Say, for example, if you consider the algebra SU11,
there is such a compact form UQ SU11 when Q is some real number. Now H is real. Then if you will ask about the classification of unitary representations, you will have the same unitary representations as for SU11. You will have principal, complementary series, discrete series, and on the top of this, there will be one series which will have highest weight more or less this, some real number plus I pi over h. See, because it's I pi over h, this is exactly sort of the piece of information which is missing when you consider formal neighborhood of 0. But it exists for real h. And it's interesting that the Plancherel measures, for example, if you will do something like harmonic analysis for these algebras, there is a way to do it. It will, well, so some elliptic functions will appear with this module, and there will be some strange action of the modular group on these values of Q. So what I'm saying is that there is something very interesting for there's some interesting and basically very little known about this. There's something very interesting in the theory of unitary representations of non-compact real quantum groups. So this is the end of this preliminary formal informal talk, and next time I'll say the following. I'll say a few more words about simple about quantized universal enveloping algebras for simple Lie algebras. In particular, I will explain that there is an isomorphism of the Grothendieck decreeing for the category of finite dimensional representations over these algebras, and the center of this quantized universal enveloping algebras. And then we will have the same isomorphism here, but here there will be some extra structure. On the center there will be a structure of Poisson algebra, and sort of this is the subject of the next talk. I don't want to give it now. So that's
one thing that's been in my mind as you're talking. When you start from a Lie group and you consider the representations, right? Then you have this tensor, I don't know the words, monoidal category, the tensor product with the symmetry. The commutativity is symmetric.
Yeah.
Right? And then you deform.
Wait. If you start from a group,
like SU2 or something like that.
Yes.
And then you have the representations, the tensor category, A the ordinary tensor product of the vector spaces. And they're associative and commutative. There's an isomorphism. It's symmetric. Yeah? Now, what's puzzling me, it seems to be somehow the main point, is that when you do the deformation, you lose everything. This symmetry.
It's you don't lose it completely. Fortunately, there is
You lose some of the symmetry, but you keep the, so to speak, the Yang-Baxter equation, or you keep the braiding identity.
Exactly.
Why?
Why?
If you lose it, why don't you lose it completely? You keep this. You see, in your drawing.
Yeah, let me think about it. Well,
it's remarkable.
It's
so somehow the deformed commutativity that you had becomes the braiding. You don't have to think that you would some smart guy invents Yang-Baxter. It comes.
Exactly.
It comes out of the stuff of mathematical.
It comes out from topology, absolutely naturally. Yes, it comes out from topology of.
No, it doesn't come out from. It just comes. You deform it and it comes. Right? And then it has a topological interpretation.
Yeah.
But where does this identity come from?
You mean the braiding identity?
Yeah. The deformation. And why is it true? You just take this abstract notion of a deformation.
I think I have too many answers to this question.
Oh, give me any one.
Why it is true? Well, there is a very technical answer. We want to deform our algebra, but not just to deform it in whichever direction. We want to keep it in some nice category. And in particular, deforming algebra is more or less the same as deforming category of its modules. So, in some sense, the whole idea here, when this business about quantum groups started, the whole idea was that this relation should be preserved because it's so important for all applications where it came from.
Not a good answer.
Well, that's
Because it's true. I mean, if you make an abstract definition of a form structure, it's true.
Well, here's an example of so far we talked only about braiding. We didn't talk about co-associativity, but there is a very natural. I don't know. I think the answer is the following: that there is a natural category. There is a natural class of categories. These braided monoidal categories. And basically what we do is we're constructing examples of algebras in these categories. Why these braided monoidal categories are natural? That's basically your question.
It's not my question. Take SU2. Consider it as a bi-algebra.
Mm-hmm.
Okay, now before you deform it, you know its representation theory, and it's a monoidal tensor category with the symmetry.
Mm-hmm.
AB, isomorphic. The isomorphic between AB and BA is the inverse of the isomorphic between B tensor A. And now you deform it as a flat formal Lie bialgebra, whatever, and you consider the new representation theory. And the new category, the deformed category of the representations, you still get the deformed commutativity isomorphism. So the commutativity isomorphism is, so to speak, deformed from the other one. And now it's not symmetric anymore, but it still satisfies this third order identity. Why? That's the question. It's not because you say, well, I think this is interesting, and historically we have many examples, and therefore I want to consider objects like this. Because it's satisfied. See, when you make the deformation, which is presumably unique at isomorphism.
Well, another explanation for this is the following.
You understand the question?
Yeah. Another explanation would be the following. It's not true that, say, if you just have a... Well, it's not true to say the following, that if you have just a Lie bialgebra G delta, and say you can deform the co-multiplication for the universal developing algebra in this direction delta, you will get some deformed multiplication, some deformed co-multiplication. So you will get deformed tensor product. More precisely, you will get deformed action of the algebra on the tensor product of modules.
We deform it as a bialgebra, though.
Yeah.
In the bi category.
Yeah. In this case, you don't have to expect that this coproduct will be, that this algebra will be quasi-triangular. There are lots of examples when it's not true, when there is no isomorphism at all. So there is a very special class of Hopf algebras, exactly these quasi-triangular Hopf algebras, when it's true that there is this isomorphism between V tensor W and W tensor V. And also there is a construction. There is a construction how to go from any Hopf algebra, any bialgebra, to a quasi-triangular one. It's called so-called double construction. And this double construction somehow gives you a canonical way to construct this algebra with the braiding element, out of any Hopf algebra. And well, I would say my third answer to your question would be the following, that in general this is simply not true, that when you deform you preserve this property. However, there is a canonical way of preserving it. And still I think
So you're saying the equation has to be put in somehow.
yeah, it's not actually there.
I was thinking that there's this analytic deformation of the structure, and it's just the symmetry equation breaks down, but the braiding equation stays.
No.
But that's just a particular. You say that
Just a way.
can't be characterized without putting in this equation. I thought there was some canonical deformation in which the braiding appears.
No, there's a.
Preserve what? Yeah. Okay, he's saying now it does appear. Okay, so now
I disagree.
I'm alive. Okay. That's what I asked. So
Yes. Yes, maybe I misunderstood.
yeah.
Let's say you have a Lie algebra.
Let's
A
say
Lie
you have
algebra.
SU2. Let's say you have SU2.
But this is a very special case.
I don't. That's the case I want to understand.
Okay. Yes.
What? Reserve what? Yeah.
Uh-huh.
Changes the multiplication in such a way then from associativity to this special information you get the outline.
Why is that? So why is that?
Because of associativity and a condition that you don't change that. You preserve form.
Well, sort of. Yeah, I understand what you mean. I understand what you mean, but if you will say it in this way, it's completely. I think it's almost misleading. But I understand what you mean. Yes, if there is a, yes, what Leon is saying is the following. That, yeah, it's a theorem. True.
Okay. Well, okay. Repeat.
I give an interpretation of what you say. If there is a G invariant, non-degenerated bilinear form on the Lie algebra, then you can do it.
What? You can't talk to him. Talk to everybody. Forum.
Yeah.
Not necessarily. This is
I have to try.
you take, triangular case. Then for any previous real,
Yeah.
there is harmony. There is young one. Start
Okay. You're right. Yeah.
but again,
But this is a very special. Again, this is a very special case. Yes.
then the answer is the following. There is a very special information. There is a variety of all information. You have no young one. But if you have a certain time, such that the one structure is fixed, either
The code structure is fixed.
yeah,
You're
either
deforming the
multiplication
I-
the phi algebra. So
I don't think it's true in this generality.
well, let's get the statement out. First.
Okay.
Yeah.
Yeah. Is it true?
Well, is it true for SU2 and why? I mean, that's really
For-
the question.
For SU2, it's true. I agree. Why it's true? Wait. So you're saying that if you have a Poisson-Hopf algebra, if you fix the co-multiplication,
You have a deformation. which
and
fixes the
if you have a deformation which doesn't deform the co-multiplication, then you're saying that there exist R matrix.
Right.
No, it's not true. No, not true.
No,
He
but
doesn't have this
wait,
theory.
Before you argue about the generality of the theorem, my question is, if it's true in one case, like SU2,
Yes, it's true in
why is
SU2.
it true? Why is it true? Because this is saying that you're creating this very interesting topological structure, named the theory of grades, out of an algebraic construction. So I can create
No.
free space out of two space.
Well, I have two statements.
I mean, that's very...
No, I have two statements. First, in this generality, for arbitrary Hopf-Poisson algebra, this is not true. For quasi-triangular Poisson-Hopf algebra.
No, triangular, starting from...
For triangular.
For triangular.
Yeah, start from triangular. Like SU2 is triangular.
For triangular is a
Well, if it's quasi-triangular, I will buy it, yes.
for triangular.
And for triangular, yes.
Triangle is all.
Yes. Yes. Yes.
One triangle is not.
No, I asked it for triangular, because I said classical
Triangular
Lie group.
is a theory. And it follows from association.
No, but still I think it's no. No, something is wrong.
doesn't belong to.
In the classical case of Levi algebra, somehow has the grading.
Yeah. For semi-simple and for Frobenius. Yeah.
Well, you're the one who planted this idea in my head last time, because you gave this, in the last informal talk, you explained how to take the Riemann surface, and you take the algebra generated by the closed curves of isotopic that has a Poisson structure, and then when you quantized it, you get grading invariance for links, so that somehow in that quantization procedure, the grading identity appears. You didn't put it in, it sort of appeared.
I can draw some pictures. Sort of.
Yeah. Yeah, okay. Okay, fine. This is what I'm really after.
Let's say.
Erase one. Needed it.